Okay, we'll have a look at a grain problem here where we're given the stowage factor of the grain, our initial displacement in kg, and we're going to load all 5 lower holes full, and then the tween decks are going to be loaded as mentioned here. And it tells us the stability data booklet provides the necessary information for these holes. Using the KN tables to construct a GZ curve, determine whether the vessel complies with the minimum criteria specified. Well, before we start, let's look at what the minimum criteria is for our vessel. Minimum GM 0.3, heel due to grain shift 12 degrees or the angle of deck edge immersion, and the residual area under the GZ curve between our heeling arm curve and the actual GZ curve itself, minimum 0.075. The other requirement, which isn't a mathematical number, is that the vessel of course must leave port upright, so she mustn't be listed at all. Okay, so first thing we have to do here is draw up our table, and we write down all our holes, not forgetting the initial displacement. Common mistake for students, but don't forget the initial displacement. From the tables, look up the capacity, the grain, the other tables which are better here. We'll go to the grain capacity, the volumetric healing moment, and the kg. So they're the values we need for this problem. All the holes are full, so we use the full values. A couple of the tween decks we have ullages, so we need to look up the ullage and the corresponding value for the ullage, go across and read off volume, grain, volumetric healing moments, and the kg. So we've gone into the tables and we've read off all those values. So we've got all our volumes written down here. We've then divided these by the stowage factor. Always divide the volume by the stowage factor, that will give you your weight. Multiply the weight by the kg to give you the moments. Total moments divided by total weight will give you the final kg. So this particular table here, these 3 values, it's fairly standard, weight, kg, moments. So that's your final kg, which is an important value, the final weight, and you must add up all your volumetric healing moments that are going to be potentially created on the vessel. And we write those down there. Now the question asks us to draw up a GZ curve using the KN tables. So when we look at the KN table, we can see that we need, with the weight of the vessel, we can write down the KN values at these various angles, 12, 20, 30, 40, 50, 60 and 75 degrees. We can write at all those angles. At our displacement, we can write down the KN values. So that's the first thing that we would do. We'd write down, there's the angle of heel, there's the KN values. And we know that GZ equals KN minus KG sine theta. And if we were to look at our stability formula booklet, it tells us there that GZ equals Kn minus Kg sine theta, and that's the only time you use this GZ formula is when we're going to draw up a GZ curve. So we've got the various Kn values. So here we'd say Kg, which is final Kg of 7.45 multiplied by sine of 12 degrees gives us that value. Subtract it from the Kn, and that gives us the GZ at 12 degrees. GZ at 20 degrees, 30, so again Kg, so that'll be 7.45 sine 20 degrees, 7.45 sine 30, so on and so on. And then we write down all the GZ values. We can then draw our standard GZ curve. We've got the GZ values along the y-axis, the angles here 10, 20, 30, 40, 50, 60, 70. Don't make the mistake of putting the 12 degree angle at 10. Make sure when you've got your scale you actually have this value at 12 degrees. So we mark off 12, 20, 30, 40, 50, 60 and 75, and there's our GZ curve. Now this particular one here is what we call our healing arm, or that we get with the values of lambda. Now if we look on our formula sheet, we'll see that lambda at 0 degrees is our total volumetric healing moments divided by the stowage factor times the displacement, and lambda at 40 degrees is lambda at 0, which we've just calculated, multiplied by 0.8. It's 0.8 because cosine of 40 degrees is 0.8, but that's by the by. So we get lambda 0, lambda 40, we get these two values. And as we can see here, we've written down, okay, lambda is our healing moments 6391. So we've got this here, 6391 divided by stowage factor 1.65 times our displacement 0.22, and then at 40 degrees 0.8 times 0.22, 0.17. So what we did on our graph here, at 0 degrees 0.22, 40 degrees 0.17, we drew our line straight across. Where the two intersect here, we would come straight down, and that is the angle of heel due to grain shift. That angle cannot be more than 12 degrees. So we'd write that value down in our criteria table at the bottom, and we can see 12 degrees. So at the moment it complies. The other thing we need to check is the deck edge immersion. And if we go into our table for the angle of heel data with our displacement, we can see that the angle of deck edge immersion is 18.2 degrees, which is far higher, so nothing we need to worry about there. Also, while we're there, we'll just look at the angle of flooding, 40.6 degrees. So we know that that's okay, heel due to grain shift. The GM, we can soon calculate or work that out because we know our final kg. We can go into the tables with our km, with our displacement to get the km. So we went into the tables with our displacement to get a km of 8.4, subtracted from our final kg of 7.45, and we can find that our final GM is 0.95, so that complies as well. So as things stand, the first two values, the GM, which we obtain with our final displacement, km and kg, and our heel due to grain shift angle, which we got from the table here, we can now know that the first two criteria are fine. Then it's the residual area we need to look at. Now the residual area is this area from all that there. Okay, we determine this value here. This is either 40 degrees, the angle of flooding, or if we draw a tangent to this curve here and go across the highest point, and we can see that it actually is there, the highest point. So the highest point is actually going to occur on this particular graph at 38 degrees. So as we draw this curve, we can see that it's slightly higher at 38 degrees than it is at 40. So what we have to do then is work out the values using Simpson's rule. So we'd write down our Simpson's multiplier, 141. The ordinates, we've got 0, and then we've got from at 20, so that's at 12 degrees. So 12 to 38 degrees, that gives us 26 degrees between the two. So half that is 13. So 12 plus 13 is 25 degrees. So we would read the value of 12, 25, 38 degrees. 12, 25, 38. Okay, so from there, 12 degrees, 25, 38, that's what we're looking for, that area there. And we have to use 12, 25, 38 because the common interval has to be the same here. So we've written down the values of the ordinates. 12 degrees is always 0, because that's where it starts, of course, on the curve. 25 and 38, the ordinates. Don't come down to the base here. Always just use this value here from the healing arm curve up. Multiply it by the Simpson's rule, get the product of the area, use Simpson's rule, which is on the formula sheet, a third times 13, which is the degrees here, 12 to 25, 13 degrees over 57.3. Remember, you always have to use 57.3 because we're dealing in degrees here and we have to convert to radians. Multiply by the product area and you get an area of 0.103. So you can see the residual minimum is 0.075, 0.103. This vessel complies. So you have to be just excuse me, a bit careful with working out these values here. You've got 12 degrees, 38 degrees here, so we have to go from 12 to 38 when we're using Simpson's rules, and we have to ensure that we have a common interval between the two. These two values are the same. So 12 to 38 is 26, half of that is 13, so each of these two halves, if you like, are 13 degrees, the base, common interval. 12 plus 13 is 25, 25 plus 13 is 38 degrees. That's where we get those values from. And you must always divide, when using the Simpson's rule, by 57.3 when we're dealing with degrees. So it's a fairly long-winded problem, but that's how we would solve it.